All right. So for our next speaker, we have a triple. We have Rob Mahony and Peter Van Gore and Sean Gow. So we've got three speakers swapping between three laptops, which will be exciting. And over to you, Rob.
Thanks very much. Yeah, so I'm a professor at the Australian National University here at Canberra, and I work in aerospace to a certain extent, robotics and aerospace. And so really, we've been involved in the ArduPilot community because we're working on some of the latest theory around the world in state estimation for vehicles. So I've got a small group at ANU, and in fact, Andrew is part of our group. He's a...
Share your screen on Zoom.
Is it shared? I thought it was.
No, it's not on the screen, but not shared. So do a share screen in Zoom.
Has Zoom died on me? That's what it looks like. I look like I've died Zoom.
It's connected to the hotel Wi-Fi, or
no, I'm on my, that's what's happened. I've walked out to the loo and I'm not on the hotel Wi-Fi, so I took my phone away. That was a silly mistake. Sorry about that.
No worries.
So it was also well organised, and then I was going to show up Paul, you see, and I failed at the first. I'll skip very quick. I've actually got to get onto everything. So is this connected?
Give you the Wi-Fi password.
No, that should be okay. I should be here. That's the one I need because that's going to get me into the Zoom. Can't check the safety of the website. Skip verification. Connect Wi-Fi. What's going on here? I'm going to the wrong Wi-Fi.
You just connected to the Wi-Fi, but it's not.
Yeah, okay, so it's connected to the wrong Wi-Fi. Got you. Why is that not coming up on this one? Okay. Got you. Okay, thank you. Sorry about that. One of these should be working, right? There it is. Yeah. I was just thinking if I tap again, I'm just setting things up to be okay. Don't want that. I want to got that. Got that. So that should get me back on Zoom. Is that correct?
Better.
Okay.
Better.
So apologies for that.
All right, down again.
Sorry, guys. All right, so we have a small group at ANU working on this, and Andrew's part of the group, and we work very closely with Andrew, and so that's starting to build up now, and we've got a number of students who are starting to get involved in the ArduPilot community and create that link between the academic end of things and this much more applied community. And that's quite a challenging link to breach across. So I'll talk a little bit about that. I've got most of the students here, so if any of these people you're interested in talking to, come and have a chat to us. And I've got Peter and Sean who are going to jump up later and talk to things. So I won't talk a lot about the group. I just want to give you a bit of a high level of some of the things that we're doing. What we're really trying to do is work in this space between the formal state estimation theory that's out there, which really is underpinning some of these algorithms like the EKF3 that are on ArduPilot, and some of the new theory that's coming through in the academic community around some new geometry that should allow us to improve, in particular, the robustness of some of these algorithms, right? So the existing theory, which the EKF3 is built on, is very good at operating when everything's working. So you're not going to do any better than our existing ArduPilot state estimators when it's working. But as we all know, if you try and do the EKF3 on a drone that's doing acrobatics and other things, sometimes it breaks. And why does it break? It breaks because you push the system outside of the linearization domain of the filter. And it's in those situations where there are advantages that we want to try and translate across into the ArduPilot community. So what I've got is a couple of minutes that I thought I'd just go through and talk about some of the stuff that we've done in our group, which is sort of a little bit touchy-feely and everyone can enjoy it. And then I'll pass across to my students and they can tell you a little bit more about the specific stuff that we're trying to do in the next year. But we're always there, and if people are interested in these things, then they're welcome to talk to us. So this is an interesting vision-based problem. So we treat cameras as a sensor for robotic systems. So that's where we're coming from. And here we're tackling a vision problem, which is a challenging one, underwater vision problem, but where you've got an assumption of flat ground. And I'm interested in this also in the ArduPilot community because there are often situations where an aeroplane or a quadcopter is high enough up that a flat ground assumption on the ground is actually a really good thing to do. And what we've been doing in that particular piece of work is studying homographies, which use that flat ground assumption and creating estimations of those homographies, which you can use then for navigation and things like that, that are very, very robust by actually treating it as a state estimation problem and not as just a computer vision estimation problem. And this example that you just saw run there is nice because it really demonstrates the failure of the traditional approach. So what we're actually doing there is we're using the previous estimate and we're running an actual filter, whereas if you try and estimate from frame to frame the correspondences in the vision, then you get a lot of error in these challenging situations where the fish are swimming across in front of the screen. So that's a nice little piece of work. This is a piece of work actually done by Peter, which is sort of state-of-the-art visual inertial odometry code. And it's very, very similar theory behind this to the T265, that the Intel sort of visual odometry camera. And one of my goals in the long term is to translate some of this visual inertial odometry theory across into the ArduPilot community with a system that's really, really solid and robust, and you simply sort of put the camera on the vehicle and it works. This is a data set from colleagues in Zurich, University of Technology Zurich, and we've got some really nice results on these sort of situations, just flying in a room with a Vicon system. We have talked to some people in the ArduPilot community, and we actually had a project with Michelle a few years ago where we were trying to start the translation of this. What we did was we learnt a lot of things about the real difficulties of doing visual inertial odometry for vehicles in ArduPilot community. And so that's been a really powerful learning experience for us in academia and is shaping a little bit what we're trying to do research-wise. Go ahead.
So can you expand on that? When you say difficulties, is it difficulties because of our architecture or the use cases that we typically go into? Or
primarily use cases. So the thing that we found was that when we actually put it on vehicles and you flew up 30 meters from the ground and all of your points were sort of on the ground, you weren't embedded in the environment, the sort of approach that the academic community has taken doesn't work so well. Right? And so what I'm looking at is going to additional priors. So when we say prior assumptions, things like, can we sort of assume that we've got some flatness in what we're looking at when we're high above it? and start utilizing that. So that's why the holographies are interesting to me. But if you do classical, in my opinion now, having done that piece of work with the archipilot community, if you do classical academic VIO for an archipilot, you'll always have the sort of problems that we saw with a T265, right? That approach isn't sophisticated enough to deal with the use case scenarios where you're basically flying along above flattish sort of things and too far away. If that makes sense, yeah. So, I mean, and that's exactly that example that I just showed you where you're inside a room and everything works really nicely. Yeah, and we can do that. So can lots of academics. And what I'm gaining is an appreciation of what the real problem is. Yeah. And so that's one of the reasons why I love working with this community. I'll stick this up because there's actually some really nice code available for this. So one of the things that I'm really interested in is using vision in aerial applications. And so one of the things we wanted to do was get high quality, high density optic flow and use it not just as a visual sensor aid, which is what you can buy commercially, but actually use it for navigation and for obstacle avoidance and things like that. And so I did a project about 5 years ago with a student, Juan Adav, who's now in Colombia, and has gone ahead and developed that into the Luvia project, which you can see down the bottom. I don't think I can get rid of that. I'll move that across as maybe up there where it's hidden. So the Luvia project, and what he does is use essentially a GPU implementation of some theory for optic flow. I won't tell you about the theory that we were doing in that application, and it has its advantages and disadvantages. So we get dense optic flow. We're running that at 10 millisecond time slice on a GPU. And it would probably run at something like a 20 or 30 millisecond time slice on a Jetson type GPU. So that's running on a computer. So there's a potential with that sort of code to really sort of compute not really accurate optic flow, but decent enough optic flow that you can actually do navigation in forests and obstacle avoidance and things like that. So obviously I'll save these slides, and I guess this is just a bit of a plump for that code that you're very welcome to use. Some of the things that we've done with optic flow, and I guess I put this one in simply because it's sitting there in the background. So in 2010, actually, we worked with the Commissariat l'Énergie Atomique en France, and we were looking at just some basic optic flow stabilization, so using the optic flow to stabilize. So that was nearly 15 years ago now. So I guess, but I just thought it'd be interesting to actually see the original videos since I have them. And then we were also looking at some of the things you can do with optic flow, where you actually can land a vehicle on a moving surface and stabilize the optic flow. So that was all work that came out of my lab about 15 years ago. This is a little bit more recent, where we were trying to actually use Juan's algorithm to do actual navigation of a quad. So what we've got on the bottom left is the actual optic flow measured. So you can see the optic flow field there on the bottom left. In the middle is a navigation control. So I'll make sure this is cycling. I might have to keep clicking to start it. I think I forgot to cycle it. So the middle image there is showing you the actual velocity of the robot plotted onto the plot with a light grey, and the target with a bright white dot. So you can basically see from the optic flow, you're computing a target direction that you're trying to fly, and then the actual direction that the quad's trying to fly. So you can see those two dots moving around. And so what you can see is, as the optic flow shows you that you've got an obstacle, it's giving you a steering command to move the quad into another direction. And the right-hand bottom is the cost criteria that we were using based on magnitude of the optic flow, essentially in a divergent field that we were trying to minimize. So I guess you guys have all seen some of the different vision-based avoidance strategies. This was one that I was working on academically. There's a lot of insects and animals that use optic flow to control what they're doing. One of the interesting things I sort of learned, I'm giving you a history of all of my failures here. One of the interesting things that I learned about that is that optic flow is actually, although it's very good for insects that are very, very light and essentially can control their velocity extremely well, it's not a great input directly for vehicles with a lot of mass. So what you find with optic flow is that it's extremely strong when you get close to something, but it actually doesn't increase in intensity as you approach an obstacle fast enough for good control. So my intuition about using optic flow directly as a control for obstacle avoidance is that it would be better used as an engineering input, as an input to a state estimator that then tells you how to look ahead to control than as a direct input to the control, okay? And so that was the intuition that I got out of those few years of looking at those control algorithms, okay? So when you land a quadrotor with optic flow, it tends to be a pretty hard landing. It'll come down quite fast and try and slow down right at the end and try and land. And it will land, right? Especially if you can control the velocity properly. But you've got a lot of momentum that you're trying to get rid of right at the end in the with the rotors. And if you actually do an MPC control or something, a more sophisticated control, you'll find that you won't follow that trajectory. So I didn't want to waste a lot of time, but I thought there's a technology out there, vision technology, which is just really cool. And I thought I'd take this chance to tell you guys about it, because I think it's something that's really interesting and will really make a big impact in aerial robotics over the next 5 years or so. So this is a thing called an event camera. So a traditional camera is set up so that at a specific time point, you open the shutter on the camera, and then after a certain amount of time, you close the shutter, and then you measure all the intensities of the pixels in that particular image. So an event camera is made differently. Every single pixel on the camera has the same photodiode as a standard camera, but behind that, it has a set of electronics, which is doing comparisons all the time of the amount of light coming in. And what an event camera does is it generates these events. So whereas a normal camera takes intensity at every pixel at a time slice, an event camera, so that the actual image here would be these little black dots on the image. What an event camera does is every time the intensity changes at a pixel, it generates an event. So you get information all the time, right? So, and that's what comes out of an event camera is this stream of data, and each event tells you at that particular pixel, it's got a little bit brighter, and it gives you a timestamp when that happened. So the advantage of event cameras is it does things like it gets rid of blur because it sees the change in intensity at a specific point in time. So you don't get this integration over a period of time to get the same event. So one thing it's really good at is getting rid of blur. Another thing it's really good at is because every pixel is independently tuning its gain effectively. There's no global shutter speed. There's no global exposure time. And so it's very good at dealing with big differences in dynamic range. So if you're putting a camera on something and you've got the sun and you're trying to look into a dark underneath some trees or look somewhere where it's dark, then event cameras are really, really good at dealing with those differences in intensity. So one of the things that we've done with it is we've put it together with a camera. And so on the top left is the actual output from a camera on this drive through Zurich again at night. And so that's what you get out of a normal camera. And part of the issue is that the camera's intensity, its exposure is being set for the bright lights that it's seeing. So you're not seeing much else because of the camera. And then we've got an event camera. We haven't shown you the actual output of the event camera. And then you can ignore everybody else's algorithm because ours is the best. So the bottom right is the algorithm that you can sort of compare it to. And what you can see is that by using these two data modalities, you can actually generate a lot more information. Again, here, this is actually down by the sailing club at ANU, where during winter, about 2 years ago. So you can sort of see the ability to bring out the trees. You can see a little bit more texture. These are older data sets and the data is not quite as strong. So it's a really powerful output. The video I'm showing you here is actually positive events in blue, negative events in red, just to give you a feel for what an actual data set out of an event camera looks like. So you only see motion. So you can see there's nothing in the background because the camera is stationary. So you only see what's actually moving in the scene. And this is Michelle's quad. So you've all seen Michelle flying her quad acrobatically. So what we did was we put Michelle's quad up in the air and we've used an event camera and we're using a very simple little tracking algorithm to be able to actually see the quad moving in the air. So what you're actually seeing here is because the quad's got rotors, it's flickering. So where the rotors are, you're getting lots of flickering information out of the quad, and then we're able to grab that information and pull it back. So I just thought it'd be really interesting for everyone here to sort of see a couple of those outputs that we're doing. All right. So that's enough about me, and I apologise I've taken probably more time than I should have, but at least a few interesting videos. What we're really trying to do at the moment that connects best with the ArduPilot community is around state estimation. So way back in 2005, I can actually put up this original work I did with Bertin Technologies in 2005, where we did the original filter that went into the DCM, which has been improved many, many times in the ArduPilot community. But that was actually the enabling technology that was able to make these original sort of UAVs in 2003, 2005 actually work in practice. The EKFs at that time, the sensor systems were so poor that you just couldn't get the EKFs to work. And I've showed you a little bit about homography and visual odometry and stuff. What we're really interested in at the moment is the inertial navigation systems, because we think we've got some contribution which is exciting to the ArduPilot community. And so this, Sean will talk a little bit more about this particular algorithm, which is what we call an EQF, and he'll explain what an EQF is. But it's a variation on the EKF using some geometric input. And what that gives us, as I said before, is these 3 points. There's really 3 things we think we can offer the ArduPilot community. One of them is a lower linearization error in the large. So we're not going to improve things when the filter, the EKF3, is working well. It's going to be the same. But what we're going to do, hopefully, with this lower linearization in the large, is improve basins of attraction. We have this global error definition, which means that we're going to see improved transience of filters. So the actual, if something goes wrong and you have to reset a filter, it should improve more quickly and it should converge more quickly. And that actually translates into, if we put calibration states and such like into filters, we're going to get better convergence of those things. And the other one, which Peter's going to talk about, is we would like to replace the DCM because we think we can build something that's very similar to the original complementary filter we built that went into the DCM that actually does the same thing for INS. And we've only just recently figured out how to do that. So there's 2 slides now, which are what I'd like to do with the ArduPilot community over the next 12 months. So one of them is a new filter that I've sort of labeled SINS 1. So that's sort of the first of 7 versions of SINS that we're going to develop at ANU. Well, anyway. So this would be a replacement for the AHRS module. So this is a replacement for the module that runs in the background on ArduPilot, which is the default that you run to when the EQF fails. And so the idea of this would be, it would be improve the performance and the dead reckoning capability of the AHRS without compromising its robust. So there's two things you can do with filtering. One of them is you can try and improve the performance, like the actual quality of the estimate when it's working. And the other one is you can try and improve the robustness or the ability of the filter to never break. So if you get a fault in a sensor, the filter will still work. And those two things actually are contrary indicators. I don't know if that's the right way to say it. But if you make a system that tunes the gains very aggressively to get the best possible accuracy out of your results, it always tends to compromise your ability to be very robust if something breaks. Similarly, if you tune an estimator to be really robust and just sit in the background and never break, it should never be able to perform as well as something where you take the linearized performance and really tune it to do what you want. And so I think that, and ArduPilot has that, right? Because it has a DCM that runs in the background, which is what you rely on if something breaks in the EKF, has the EKF, which is very high performance. And so that's what we want to do. We want to split this up. So this one, we've got the two students, Punjaya and Patrick here, and Peter, who are sort of leading this project with Andrew. Hopefully within 12 months, we can do something that'll be a really good replacement for the DCM. And the other thing that we want to do is look at the EKF and see if we can actually translate some of this theory we've been doing and build what I want to call an EQF1, which would then be competitive with the EKF in the ArduPilot community. And so that the goal of that would be improve the robustness. It wouldn't still be guaranteed robust, which the SINs should be, but hopefully without compromising performance. And so hopefully Richard will be part of that project, and Paul, and then Peter and Alessandro from Klagenfurt. So what I'll do now is I'll hand over to Sean, and he can tell you a little bit about the second project. And so that'll now be a screen share swap for you, Andrew, if you want to do that.
Yeah.
Cool.
And can you, Sean, are you screen sharing?
No, not yet. Just give me a second.
Right. You're now a co-host.
Yep.
It's fine to go a little bit over the hour. Absolutely fine.
Okay. Then I need to share my screen. Screen, it's got to.
Right.
Is it being shared?
Yep, got it.
Cool. No. Right. Thanks, everyone. So I am a PhD student of Rob from Australian National University. So I'm going to talk about our recent progress on filter design for inertial navigation systems. This is a joint work that we did with our collaborators from University of Klagenfurt in Austria. And as Rob said, this piece of work is where we really try to push the performance and do some really accurate filtering for inertial navigation systems. So to better explain the motivation behind this work, I'd like to take time to briefly go through all the backgrounds of INS and what states that we care about in INS problems. So first of all, the attitude, we want to estimate the orientation of the vehicle in the inertial reference frame. whether we're modeling it using all angles, quaternions, or rotation matrices. Then also we want to estimate the robot's position and velocity in the in the inertial reference frame. And more importantly, in practice, there will be bias in the IMU data that we receive. So that will happen in both the angular velocity and in accelerations. And recent research also want to accurately estimate these bias parameters so that we can get really good performance. Then apart from that, in some problems, we also care about the calibration states. For example, the sensor lever arm position in the body fixed frame. If we have a sensor like a GPS receiver rigidly attached on the vehicle, but we don't know its exact position with respect to the IMU, then we would like the algorithm to help us do online estimation of those states. Okay, so now let's have a look at how different algorithms solve this INS problem. So the earliest work is the classical extended Kalman filter. It uses Euler angles to parameterize the attitude of the vehicle. So basically, the full system is being modeled on a flat space called the Euclidean space. But as you know, the Euler angle parameterization has its own limitations. So that's why from 1980s, people start to use quaternions to represent the attitude for the filtering problem. And that introduced the multiplicative extended Kalman filter, MEKF. It has been the industry standard solution for nearly 30 years. Then more recently, motivated by attitude estimation on micro-aero vehicles, people found that the attitude can be naturally modeled on the special orthogonal group, SO3, which is the Lie group of rotation matrices. And this leads to the complementary filter, which is being used for DCM module, and also the invariant extended Kalman filter, which is a general filter design for systems on Lie groups, such as rotation matrices. And then there are also a series of other geometric-based filters. So if we do a comparison of how different filters model this inertial navigation system problem, the classical EKF is modeling the full state as a vector. So it doesn't consider any geometric structure of the system. So as you can see, the Euler angles, which is just the R3 vector, then same for the position, velocity, and the bias. So everything is flat. There's no geometric insights in this. So then in the multiplicative extended Kalman filter, we start to use the quaternions to model the attitude. So now the attitude part has a group structure. But for the rest of the states, they are still just being modeled individually as vectors. Now, if we go into the invariant extended Kalman filter, we start to use this very nice Lie group structure called SE23. So that is where you can basically model your attitude as a rotation matrix R, your position X, and velocity V all into a single matrix representation. So this is a 5x5 matrix. Well, what that parameterization gives us is a very nice property, which called the group affine. It basically means the system linearization is exact. So there's much less linearization error when we do EKF using this parameterization of the state. However, there's a major limitation of this formulation because the SE23 group structure can't deal with the bias in the system. So what the IEKF does is it extends its state by modeling the bias as an R6 vector, an element on the Euclidean space, then do a direct product to couple these two states together. And that actually breaks the nice property that SE23 has, which makes the filter imperfect. But after all, this filter still outperforms the MEKF. So that's why it has become the state-of-the-art INS solution for many years. And if we just stop there and look at from EKF to IEKF, there is a clear trend here that every time, well, I missed that. So up to IKF, we can see that there's a clear trend that since the classical EKF, every time there's a major breakthrough in the performance that you get from those filters, it's because people find a much nicer way to model the system state. So now what we propose, the equivariant filter, EQF, as you can tell from the table here, we introduced this new geometric structure. So on top of that SE23 formulation, we found that the bias in a system which, so there are the part for the angular velocity and the part for acceleration that can be naturally modeled as a single element on little SE23, which is the Lie algebra of that SE23 Lie group. Well, I'll talk about that in the next slide, but obviously this has a single matrix representation. And basically now what we have is a global matrix parameterization of the four states, including navigation state and the bias, just into one model. And then we will do the standard, well, we will do the filter on top of that parameterization. So here's what that means for us. We model the navigation state, rotation, position, and velocity on the same SE23 Lie group. And the bias is being modeled on the Lie algebra. So if you imagine this sphere on the right is a Lie group, then the Lie algebra is that tangent space, that the plane that is tangent to the sphere. So we find that the bias can be naturally modeled on that tangent space. And what that gives us is then we can couple these two matrices using what we call the semi-direct product structure. And that gives the parameterization of the four state. So that's SE23 semi-direct product with the little SE23. Now, what this gives us is the group structure lets us to find a globally well-defined error, which is fundamental in those high-performance filter designs. And unlike the other approaches, now in this model, the navigation state and bias are now tightly coupled, which gives a very nice geometric structure. And it also reduces linearization error in the filter. So at the end, this improves efficiency and makes filter converge much faster and more consistent. So here are some experiments that we did with this algorithm. We first run it on a simulated data with onboard IMU and GPS measurement. The calibration state, which is the position of the GPS in body reference frame, is unknown. And then the next experiment is a public data set shown on the right. So it's a drone racing recording with high speed and aggressive motion. We also do in-flight filter reinitialization just to simulate a situation when the filter is turned on during the flight at a very high speed without having any idea of the current state. So here's what we got. On the left is the simulated data where we know what the ground truth of the bias is. And on the right is the result of the real data set. Basically, we do this comparison with the MEKF, the multiplicative extent common filter, and IEKF, and the latest version of IEKF, which was the state-of-the-art INS solution before we published that. The most performance gain we get is in the filter convergence and consistency. So it's more obvious from the right figure when we do in-flight reinitialization of the filter has no idea of the current state. So the initial error is always super large. And our filter, which is in red, is converging faster and also behaving much more consistent during the convergence. So this is pretty much everything about this filter. And next, Peter will talk about a more robust derivation, well, a more robust solution to this INS problem. Peter. Yeah.
So can we just swap over
sure.
and let Peter set up?
Mm-hmm.
And then you can stand here and answer questions.
Yep.
Take it off. Walk away. Give him space. Good. Thank you. Sorry.
So yes, the equivalent is, well, it's a good personality, so it's always very computational efficient, sure. And compared to EKF, I think we are well, not slower than EKF. But yeah, we haven't done very well quantitative pricing. You know that it's forming shared cost.
It has the exact same algebraic application.
So similar amount of mathematics calculations.
Yeah.
The current version has a lot less states, so it's only doing GPS position. The CL method on GPS position and IMU, so not using both velocity, magnetometer, barrow, those types of things. So there's less going into it, which should hopefully mean less computation.
Yeah, although eventually we'll probably.
Yeah. Hopefully you guys can join us for the lunch or the dinner.
We're here today, all of us.
Right.
Yeah. So you can talk to us. The answer is the issue, so it does the aerospace stuff that you want. The issues you ran into were in the coupling. So they're, and we don't get it because we've built the global geometry. And that's why I wanted to do it. That's the pot of gold at the end.
Fundamentally, any with a different parameterization for these things that you're talking about, how to or bias.
Yes, so our goal is to get based nodes. But just similar to NPM or IPF, we're just choosing different parameterization of the states, right? By increasing more geometric insights into how we parameterize the states and get a better structure. So
I haven't looked at the work. I'm trying to make head or tails of it and figure out how to do the derivation of filter. Way over that. Basically everybody in this room. And it would be nice to have give an explanation of the basis for this work, because it's really flying over my head. I think it's flying over everybody's head. It's a big call.
So 100% agree with you, and look, we're happy to talk about it. I sort of see our challenge, and it comes from trying to translate from academia, right? It's not surprising that stuff we're working on in the academic community is a little bit out there. What I want to do with the autopilot community is really connect with the real problems, and then spend time in this space and explain the stuff to you. And we need to do both. Because at the end of the day, I mean, if the UK is a brilliant filter, right? I mean, it's world standard. The UK3 is world standard filter. So if we're going to beat it, we need to use these ideas. But then we need to do both to make sure that we can actually demonstrate that it has an advantage and then provide the insight as to what's going on. So we're still learning how to do that.
Well, I have a filter in the data set that I would challenge here to do better on the data set.
Absolutely. use your filter, right? And that's the nature of well, I mean, there's different. Anyway, let's happy to chat anyway.
All right, Peter.
All right, I'll try and be short and sweet. Basically, we've got some really exciting new research, seriously from the last year, where we worked out a way to get the same stability and convergence properties of the original complementary filter for rotations, and extend that to the whole inertial navigation problem. So rotation, attitude, position, and velocity. So in terms of motivation, ArduPilot's of course running on a DCM complementary filter and an EKF3. The EKF3 uses linearization of the inertial navigation states as well as a few other states and all the measurements, so position, attitude, velocity, it does it all. But in the end, you can only ever get local convergence and stability. You know, if I initialize 10 kilometers away from where I should be, or if my GPS dies for 20 seconds, I might be in trouble. DCM, on the other hand, in theory at least, is globally stable. So no matter how bad your initial guess at your attitude is, the DCM should find it. But of course, it only does attitude. So if you want to know what the position or velocity are, tough luck. So our new research is, there are the equations on the right. Don't worry too much. There's a lot of Lie group magic going on in the background to make these work. But basically, it just comes down to a complementary filter for the full inertial navigation problem. So what you can see in the equations is we've got an R hat attitude estimate, V hat velocity estimate, P hat position estimate. And then we got some extra bits to make it all work. Just like the original DCM complementary filter, we've got global convergence and stability properties instead of local, like in the EKF. And there are only 3 gains to choose. So it's pretty straightforward to tune. Here's a bit more of a detailed comparison. So again, we're doing attitude, velocity, position, 9 different states, whereas the DCM's doing only attitude. We consume gyroscope and accelerometer as inputs, whereas the DCM's only using gyroscope. DCM uses accelerometer and compass as output measurements. And at the moment, our filter is using only GPS position. So it doesn't rely on GPS velocity, on compass, on any of these other sensors. And even with that, it's able to get the global convergence. Okay, we don't have any additional states, so we're not doing biases at the moment or magnetometer reference or anything like this. Whereas, of course, the DCM does gyroscope bias. We do have 6 auxiliary states, which are they're a bit like a covariance matrix, but not at all in the probabilistic sense, only in the sense that we carry around this extra state to make the filter work. But it doesn't tell you that position is plus or minus a meter. It's just a value that it needs, that the filter needs. It's like an integrator gain, sort of. Yeah, and then stability guarantees are the same for both the INS complementary filter and the DCM complementary filter. Compared with the extended Kalman filter, so we have the same fundamental states that we're trying to estimate, attitude, position, velocity. We have the same inputs, gyroscope and accelerometer inputs. And this, again, we're only using GPS position at the moment, whereas, of course, the EKF has the ability to consume GPS position, velocity, compass, airspeed sensors, baro, visual odometry. You know, there's a lot of stuff the EKF3 can do that we currently can't. We're working on it. In terms of additional states, we also don't have any, whereas the EKF is doing biases in the gyro and the Z accelerometer, gyro scale factors, Earth and body magnetic field reference estimation, northeast wind velocity. So these are all things that we have pathways to add to our filter, but we haven't gotten there yet. Again, it's very, very recent, this research. In terms of gain states, so these auxiliary velocity and position variables are all we need at the moment to be able to do our estimation. Whereas, of course, the EKF relies on a square covariance matrix, which is the size of your state squared. I mean, it's symmetric, so you could save some space, but it's still a very large matrix. So it's going to take a lot more computations to update and use this. And as I mentioned at the start, whereas we have a global asymptotic and local exponential convergence, the EKF is only providing local exponential. So what that means in practice is that I can initialize this INS filter anywhere, no matter what attitude, no matter what position, velocity I choose. It might take a few seconds, but it will get to the right answer. Whereas, of course, if I start an EKF with a terrible initialization, it's going to fall apart. So first, some simulation results. These are very academic. These are, I wrote my equations as ordinary differential equations. They're continuous time. Of course, on the computer, you can't do this. You have to do things in discrete time. This is all roughly continuous time. Nice academic example. Look at that, it works. We start with an attitude of 179 degrees, which is about as much attitude error as you can get. Velocity about 2 meters per second error, position 10 meter error, and within a short time frame, everything's converged. But again, very academic example. So in the last 2 weeks, we've been plugging this into some CITL data. Here's a result from CITL. So this is comparing our INS with the existing DCM, the AHR2, and the EKF3. And what I don't have time to go into detail the error of these things, but what you can see is that roughly at the moment we're doing a similar estimation to the existing stuff. Likewise, in position and velocity, one thing that's interesting here is, of course, we've got a bit of an offset on the down position and also on the down velocity. I'm afraid I can't explain to you why the down velocity is offset. I don't understand why the EKF3 reports a non-zero velocity when its position is not changing. As for the downward position, it seems to be associated to the barometer. So we're consuming GPS altitude. The EKF3 is consuming barometer altitude. Okay, but still, this is CITL data, so it's kind of nice. It's not a real challenge. Fortunately, we also have some real world data. So this is real world data. It's nasty. We have time lags in the GPS. We've got biases in our signals, noise, all this other nasty stuff that breaks filters. We haven't taken care of biases in our filter. We haven't taken care of GPS lag. Still works, no problem. We get a decent attitude estimation similar to the existing filters. So what I'm trying to emphasize is that this is where we are now with a filter that's written in these continuous time equations. We've discretized it as crudely as you can imagine. We haven't accounted for any lags. We haven't accounted for any biases, any of these errors that are sort of important to think about, you would think. Despite that, we're working on real data. So we're looking forward, we're expecting to only get better from here. Here's, of course, the position and velocity as well. So again, we have that offset that's explained by the difference in consuming barrow height versus GPS altitude. Just to zoom in a little bit, this is a 20-second segment from the attitude estimation. And so I just thought I'd show it off so you can see how close we are. So actually in the pitch, we're a little bit closer to the EKF than to the DCM attitude. I don't know exactly. My explanation for it is that we are consuming GPS position, just like the EKF3, and using that to aid our attitude estimation, whereas the DCM is, of course, using the accelerometer gravity vector. So wish list going forward. What are the things we'd like to do from here? We want to take these continuous time equations, turn them into discrete time equations so that we really do things properly rather than just crudely integrate ODEs. We'd like to add additional sensors. GPS velocity would be great. Compass is an obvious one to help with the attitude estimation. Airspeed would be really cool. Barometer as well. How do you balance between GPS altitude and barometer? We'd like to estimate some other states as well. So wind velocity is a big one that'd be really good to get an estimate of. Biases in the accelerometer and gyroscope should help improve our performance as well. We need to compensate for lag in our sensors, especially the GPS. So if you're out by 100 milliseconds, we can delay the filter. We haven't done that in the real world results I showed. They really are just consuming lagged GPS as if it were happening at the current time. But we'd like to compensate for that properly. And we'd also like to incorporate some of these things that are in the existing DCM complementary filter around using things like the weather vane effect, where I know I'm flying forward, so my velocity, my fixed wing velocity shouldn't deviate from the forward axis of my plane. Who have we got working actively on this stuff at the moment? There's me. I'm working on writing academic papers and working out these filter equations. And then sitting in the back, we've got Patrick doing discrete time implementation and running all these different tests for us on SIDL and real data, as well as Punjaya, who's looking at these extensions to these new sensors, or new to us. So GPS velocity, compass, these sorts of things, and including the IMU biases. Summing up quickly, we've got a new complementary filter. It's not just doing attitude, it's doing attitude, position, velocity. It uses 15 states total compared to the EKF's 600 states. That number is going to go up as we add some more sensors and as we want to estimate biases and these sorts of things, but it should still stay a lot lower than 600. And unlike the EKF, we converge from any initial condition. So we got nice results on our academic simulations, but we also have results on SIDL, and we have even results on real world data. And we're really actively working towards estimating more states like the wind velocity, these sorts of things, as well as incorporating more sensors into the framework. But we and I am also very interested to hear from this community about what, if we're going to put this in place of the existing DCM or AHR2, make an AHR3 or something like this, what do we need to do? What are the next steps?
So, like, I see this DCM as a very good system that can, bring, at least give you the initial states for EKF. Do you see that as a proper use case in case like there is a failure of existing EKF implementation, and to reinitialize it and to quickly basically reset the system state for EKF, and then continue that
yeah, absolutely.
EKF take over from there, sort of that kind of implementation. Have you played with that?
We haven't played with it, but that's absolutely a use case for this. So like the DCM, it's not going to be as locally accurate, as fast to converge as an EKF might be, but it'll work from anything. I'm just going to quickly put up my thank you slide for for everyone involved with the project. But yeah,
so one of the things that I really like about the EKF, which I'm not so fond of about the DCM, is that, as far as I know anyway, DCM doesn't report its health states to you very accurately. And for copters, at least, one of the great advantages that we got in terms of safety from moving to EKF, I mean, obviously we got the performance improvement, but it was the ability to know when things were going wrong. Because we used to have that inertial nav system paired with DCM, which was stable and would fly pretty well. People really liked it. But when things went wrong, it would just fly away. And I definitely don't want to go back to those days. So on your wish list, if you could have, health reporting or confidence reporting, that would be great.
Yeah, absolutely.
And maybe that is where, using this as an initial state for EKF, and then EKF just, continuously giving you out information is also, that's sort of baked into the system, right? The accuracy metrics.
To your point about initialization, very quickly, I ran some tests with some extremely poor initializations. So this is on the real data where we initialize with an error of about 120 degrees, and so it takes a little while, and that has to do with the fact that you can't observe the yaw of the aircraft until it starts to move. Once it does, though, we converge the true angles as well. So in that sense, yeah. So if that's the best information you've got, you can just run our filter and it will get the right answer.
far away from the goal state. You end up with the having bias states often can slow the initial evidence, but it improves the follow-on accuracy. So there's a little bit of a thought process to narrow it out, maybe not engaging bias states. Initially, it's going to be at least converged out best part of your error.
Do you want to answer that or?
No, you can go ahead.
That comes from the fact that the bias states aren't coupled tightly in geometry. So when you couple the bias states in geometry, you'll actually, and we can show you some graphs in Sean's work where you actually see the bias
Bias will converge.
move a lot quicker and converge a lot quicker because it's more tightly coupled through the geometry. It's really getting that coupled in the geometry helps exactly that.
I'm gonna leave it there because I'm already over time. But thanks everyone.